Yeah, so the very first thing to do in a geometry problem is to draw a diagram. This diagram is too small. This is why I like immutability. Okay, giant. Yeah, so we have this quadrilateral. And we want to find some point P on line CD such that the areas of this side is equal to the area of this side. And yeah, so we're choosing to define. So the way the problem's originally phrased is that there's a line passing through A, and that's the free thing. And then like that line happens to pass through CD at some point. But instead of doing that, like if we were to like literally follow how they construct the diagram, we would have to like choose some angle theta here. Oh, the pointer is not working. Yeah, we would have to choose some angle theta here or something, and then find which value of theta splits the quadrilateral in half, and then find the intersection of that with CD. So we skip a step there and we just let P be the intersection point of the line and CD, and then we just use that to define the line. So AP is the line that we've chosen. And yeah, so we know that APD equals ABCP. But ABCP is kind of hard to find the area of. So we instead use the fact that ABCP equals ABCD minus APD. So yeah, we're just solving the equation APD equals 1/2 of the total area. You can just do this directly as well. Like if you split you split ABCD into two things with equal area. So one of those things will be half of the total. And I'm not sure why I had to justify that using that equation. Okay. So first thing to do, first order of business is find the area of ABCD. There's tons of ways to do this. The way I first did it was like shoelace formula, which is like shoelace formula. The way shoelace formula works, I think most people should know what it is. You first take these diagonals and take the sum of the product. So that's like 0 times 2, 0 plus 1 times 3, plus 3 times 0, plus 4 times 0. Minus the ones in the other direction, which is minus 0, plus 2 times 3 is 6, plus 3 times 4 is 12, 0, which equals negative 15/2. Yeah, so using shoelace. Using shoelace, the area is 15/2. And you can also just get it by like dropping altitudes and then finding the areas of each trapezoid. Like the area of this should be 1, the area of this should be like 5, and the area of this last one should be 3/2. Yeah, and then summing those up, it gives you 15/2 again. Okay, the trapezoids thing is probably easier. So the area of ABCD is 15/2, so 1/2 of that is 15/4. And if we let P equals X comma Y, then we also have that the area of APD is base 4 times height Y over 2, which implies that Y equals 15/8. So yeah, now we have the Y coordinate of P, and we also know that it lies on CD, so we can solve for X. And then we'll just take this p plus q plus r plus s nonsense. Yeah, so line CD has equation y equals negative 3x plus 12, the slope negative 3. You can verify this. Yeah, you know the x-intercept and you know the slope. And next, x equals 12 minus y over 3 by rearranging. 12 minus 15/8 over 3, which equals 4 minus 5/8, which equals 27 over 8. And so thus the coordinates of P are 27 over 8, comma 15 over 8. And then taking it wants P plus Q plus R plus S. Taking the sum of that gives you 58. The most important part of this was noting that you can solve for ABCD easily, and you can also solve for the area of APD very easily by 4 times y over 2. That's the main thing to notice out the gate. If both of these shapes were very irregular, this becomes a lot harder. Like you add a couple of extra sides in there, this can get rough. Okay, but PAD is a nice simple triangle, so it's not too bad.